Well, members, we are joined today by Dr. Daniel Harrison, and Daniel is the principal investigator for the cooling and shading program of the Great Barrier Reef Restoration and Adaptation Program in Australia. He is also chief investigator for the Marine Cloud Brightening in a Complex World project that's funded by the UK Advanced Research and Invention Agency, with which we're all familiar. Daniel, our members actively advocate for the rapid development and necessary deployment of all feasible sunlight reflection methods. So you are with a group that is very, very knowledgeable and convinced of the importance of the work that you're doing. And they'll be very interested in your views, particularly on the technical feasibility, energy requirements, and financial costs, as well as the scalability of marine cloud brightening. So after your remarks, we will open up the floor for a Q&A and conversation. So let's get started. Daniel, the floor is yours.
Thank you for the introduction. Lovely to meet you all. So I'd just like to start off with two things. One is acknowledging the very, very many collaborators on this work. So a lot of what I'm going to show is the work of our larger group that I lead, my PhD students, my postdocs, and PhD and postdocs at other institutions that I also help to supervise. And then secondly, I'd like to pay my respects to the elders of the Gumbaynggirr people, past, present and future, of the lands that I work on here, but also the traditional owners, many groups that we've worked very closely with up on the Great Barrier Reef. We have a self-imposed, very hard rule in our program that we don't do any work out on sea country without the express consent and free, prior and informed consent of traditional owners, that the particular group that has, or groups that have historical rights over that sea country. And we also work very closely with the traditional owners, involving them in the research and consultation, and we haven't had a single field campaign that hasn't involved traditional owners in actually performing the research. So with that said, I'll move on to the science. I've cut the background down a lot because I did have a look at your website, and I gather that you guys are quite across a lot of the background of marine cloud brightening and the effect of the ships, sulfur in shipping fuels on the global climate. So I've cut a lot of that out, but I will give a little bit of background on the situation on the Great Barrier Reef, which everyone there may not be as intimately familiar with. But it's been a bad decade for the reef, right? So in the last 10 years, we've now had 6 severe characterized as mass bleaching events across the Great Barrier Reef. This is well known, of course, but you can see quite clearly on these maps that there's essentially no part of the Great Barrier Reef now that has been left untouched over the last decade by these bleaching events, which are, of course, caused by rising ocean temperatures associated with climate change. And so we get these not every year, but obviously increasing both in frequency and duration and intensity. We have these marine heat waves tend to occur in the summer when the waters are warmest over the Great Barrier Reef, and the waters are warm above the thermal maxima for the corals. And so they initially bleach, which is the coral host expelling its symbiotic algae, and then they can recover from bleaching depending on how long and how severe the heat stress is. But if they don't recover, then obviously there's widespread mortality, and that's what we've been seeing over the last 10 years. And those kind of events can lead to ecosystem shifts, right? And so this is just some examples of that, of the two that most commonly occur on the Great Barrier Reef. Across the top row there, there's some tidal flats with corals that are exposed at low tide. And in this case, the coral have died out and the ecosystem has shifted to being rubble dominated. And so once that happens, the rubble is loose and moving around, and it can take a very long time for that rubble to consolidate again before there's even a chance of coral re-establishing on it. But often that doesn't happen, and the sort of, because of the mounting pressures on the reef system, the ecosystem shifts and doesn't shift back. And the same thing can happen underwater there, both with rubble, but in the second row there, the example we're seeing is where probably anthropogenic influence over a long period of time has gradually raised the nutrient level in the water. And then once that ecosystem is badly disturbed and an event like a bleaching event kills off the coral, then this ecosystem shifts to become macroalgae dominated, and so or turfing algae, and then the corals cannot reestablish, and the algae takes over basically. So quite devastating for the ecosystem, as you can imagine. So here is just another way. I'm sure everybody's very familiar with this plot. The baseline temperature varies amongst some of these plots. So this one has a slightly higher baseline. But what I've done there is just drawn a very basic regression through the last, what is it now? Probably 30, 40 odd years of post-industrial revolution warming, and marked on there where we've had these bleaching events on the Great Barrier Reef. So the first mass bleaching events we saw back during El Nino events in the late 90s and early 2000s. It was the first time that widespread events had been observed on the reef, but they were not so severe. They didn't result in really major coral mortality. But then those events over the last decade I've marked on there. And so we can clearly see that we've past a tipping point for the Great Barrier Reef, a threshold where it can bleach now in almost any year. And if we put the sort of expected trajectory on there and the Paris target range, which I'm sure you're all well aware we're really not at all on track to meet, we can see how sort of quickly the situation's becoming severe for the reef. Also, and I've removed the background for this as I mentioned, but as I think this group would be well aware, the change to sulfur regulations in 2020 for international shipping has greatly reduced this inadvertent marine cloud brightening that we'd been unintentionally conducting all around the globe, and has resulted in a severe jump in global temperatures, which you can sort of see in this spike here around 2023. And the difference that you'll notice here is that these other sort of preceding spikes tend to be during El Nino years when the whole planet's a little bit hotter, but it hasn't come back down, and there's now a third point to add there. And so it's, computer doesn't want to, there it goes. And so it's quite possible that we've jumped ahead around 10 years in global warming because of this sulfur reduction to shipping fuels, and that we're now on a potentially parallel but even higher trajectory. So we've just sort of fast forwarded. And here's some of the research supporting that. It's very new. It's still somewhat uncertain. I think it's been shown pretty unequivocally that jump in temperature is due to a change in low cloud albedo, but the link back to the sulfur and the aerosols in shipping fuels is still being explored. And so far, most of the studies only sort of account for about half or so, very roughly speaking, of that change. But we know global models really don't capture aerosol cloud processes very well at all. And what I think I'd argue is that the last sort of 2 decades or so of research are really showing that clouds are much more sensitive to aerosols than we previously realized, and in many more places. Which obviously we have these very extreme examples under certain atmospheric conditions where the cloud brightening effect from those extra aerosols coming from the smokestacks of ships is very apparent, very clear, a really strong albedo change. But I think what's been largely underestimated is the more subtle but constant sort of change in the baseline to cloud albedo that didn't receive as much attention because it's not as striking as these cases. So we've done some modeling of this, the impacts of the IMO regulations locally on the Great Barrier Reef. And so this was part of an exercise to set up an atmospheric model with cloud physics for the reef and really advanced atmospheric chemistry. And so we put the change in sulfur into the shipping that goes in this. Sorry, it's blocked with. I can move that. There we go. So you can see on the very left panel there the sort of shipping corridor that goes from Brisbane up to Asia and from further down the coast on the east coast of Australia there. And so we're looking not at that global effect that this is even on superimposed on top of that, but this is just the local effect of those aerosols or the change in those sulfur-based aerosols over the Great Barrier Reef. And we found that there can be actually, under certain atmospheric conditions, quite a severe forcing over the Great Barrier Reef that was helping to keep the waters cool, but that has now been removed due to those regulations. So kind of even exacerbating the problem a little bit further. Well, it's not listening to the keyboard, but we'll go on. And so that brings us to the Reef Restoration and Adaptation Program. And so I won't talk too much about the program as a whole, except to say that it was made up essentially of some cross-cutting programs that sort of provided support to all of the individual intervention streams. And it was very wide-ranging. It was established to essentially look into everything that we can consider that might be able to help the Great Barrier Reef survive climate change. So in the very beginning, in the initial feasibility study, we had a very wide net and 140 something ideas that we considered. And during that initial feasibility phase, we sort of cut that down to 43 ideas that we considered had the potential to be scientifically demonstrated, ecologically effectively, socially acceptable, technically feasible and viable economically at scale. And so that was a real key underpinning motivation for sort of how we prioritized what we spent research dollars in the program, was that it really had to be something that could be scaled up to make a difference at the ecosystem level. And that really trimmed down a lot of the ideas, as you can imagine. So within that, we have the cooling and shading sub-program. And so this sub-program was the one that I lead, and it's established to essentially looking at all of the engineering type ideas by which you may be able to relieve some of that bleaching stress on the corals, either through relieving some of the temperature stress or relieving some light stress. And it grew to be quite large over the course of the program, so involved 17 research organisations, both national and international, up to about 70 researchers at the peak of that activity. And there's a few photos on the right there of some of what we've been up to. But I'm aware of time, so I'll go quickly. Here are many of the people I mentioned who contributed to this work. And so just acknowledge them in this photo. This is one of our annual workshops a couple of years ago. And so when we drew up the scope for this program, these are essentially the ideas that we considered were within scope. In the end, we because of prioritization and budgets and resources and time available, we focused on the two there in green for various reasons I won't go into, mostly because of their potential scalability, but also the seawater fogging was preferred over biogenic oil fogging because of sort of perceived risks around social acceptability. But as you can see, the ideas that we sort of considered reach a range of scales. And for the rest of the talk, I'll really concentrate on the marine cloud brightening research, which I think this group has a high interest in. So one of the things that became apparent very, very early on, even before RRAP, when I was looking into ideas that might be able to help the Great Barrier Reef, was just the enormous potential energetic leverage of marine cloud brightening compared to some of the other ideas that we were looking at the time, like trying to pump cold water up onto the reef, where you're putting in an enormous amount of energy to only get something back of the same order of magnitude in cooling. Whereas for marine cloud brightening, it's a completely different equation, right? You put in quite a small amount of energy to create these nano-sized salt crystals. But when one of those salt crystals activates to become a cloud droplet, it really grows up to 500,000 times or thereabouts in volume. And nature is doing a lot of the work for you. So the energetic leverage is very high, which makes it very attractive for trying to cool down an ecosystem the size of Italy. And so some of the earlier work was to really investigate this idea through modeling. Is it plausible? Could this work over the Great Barrier Reef? And this particular modeling here was apart from the upper right corner, was really aimed at addressing the question of are the clouds over the reef likely to be susceptible? You can see an example of that in the sort of top left panels there. Oops. Which where there's some cloud off of over the reef off East Queensland there, and they're associated with that bottom panel showing really quite a large increase in albedo in the model when we added extra sea salt aerosol, but also it well highlights, I think, that the primary effect here is the Toomey effect, and so it's essentially the same cloud that we're looking at, but it's brighter. It's not, you can see in those plots, it's not a substantially different cloud. And I'll probably leave it at that just because of time. And so the next step was to then look at, okay, if we have some confidence that we can change the clouds over the reef, even though that was a very new idea because nobody had really looked at cumulus type cloud regimes before for marine cloud brightening, and we copped a lot of flack for that. Everybody yelling and screaming, telling us that they were the wrong sort of clouds. But the models gave us some confidence that those clouds were susceptible to brightening, as does basic understanding of the theory and the physics behind it. But the next step was to then say, okay, if we can change the low cloud brightness over the Great Barrier Reef, would that have any effect on temperature? And so what we did was we took the actual clouds that are present, the actual low clouds that are present in the Bureau of Meteorology forecasting models, and it was this was really a bounding study. So we arbitrarily applied changes in albedos to those clouds. We weren't in this model able to actually represent the physics of aerosols interacting with clouds. This is an oceanographic biogeochemical model. So we had to sort of bracket the problem by assuming a range of cloud forcing that might be able to be achieved, informed from that previous modeling that I just showed you. And the end result of this was very encouraging, but also the sorts of levels of cloud forcing that you would need to achieve are higher than what has sort of been considered for a global application of marine cloud brightening. It's a much more concentrated area. You're only doing it during the summer, during a marine heat wave. And so to actually cool down the water that's resident in that area during that period of time, that the forcing needs to be higher, closer up to around about sort of 10 watts or so, is actually the answer that came from the ecological modelling, which comes next. So we took those results and then we put them into ecological models that predicted the future of the Great Barrier Reef under various climate change scenarios. These ones are a bit old now. We've got a new set coming out very soon. But the answer hasn't really changed at all. And what was quite apparent from this modelling was that if you look at this sort of panel in the top middle here, this is under the old RCP 2.6, so we could say something broadly consistent with the Paris targets. And the dashed line there shows the predicted trajectory of coral cover on the reef under the counterfactual scenario, no intervention, and then the solid with marine cloud brightening applied at a fairly low level in these results, so sort of consistent with one of our lower temperature forcings or cloud forcing scenarios in the oceanographic model. And under that scenario, the coral cover on the reef is able to recover and stabilize. However, what was also quite clear from this modelling was that the plot below, if you have a more business as usual type climate scenario going forward, then the cloud brightening can help for a few decades, but eventually it's overcome. And this is kind of an inherent thing, right? You can't just keep adding more and more aerosols and getting more and more brightening. It's an asymptotoping curve where you get more bang for the buck for the first extra 100 cloud condensation nuclei you add to a very clean marine system. The next 100 starts to give you only half as much of the effect, and it rapidly drops off after that. So there's kind of a window that can potentially be exploited in the clouds, and under a business as usual scenario, that window is overcome by global warming. So there's a real clear story there, I think, that marine cloud brightening, it's not a silver bullet. It's something that could maybe help relieve some of the stress on the Great Barrier Reef, but it really has to go hand in hand with obviously emissions reduction, but also quite likely other interventions on the reef to help the ecosystem. And we see that final part of the story in the top right there, where we put all the RRAP interventions as well as very aggressive control of crown of thorns starfish. Actually, I think it was in this scenario perfect control. So you essentially eliminated crown of thorns starfish outbreaks. And when you combined all these different interventions together, the model kind of went crazy. As you can see there, and the coral cover increased very remarkably. So I don't know that we can necessarily trust the numbers in that result, but I think it does show that the interventions are potentially synergistic and work together to give a greater outcome than the sum of the parts. I should mention that perfect COTS control on its own didn't have much of an effect on the coral cover. So it's really the combination. So what we really focused on, apart from, well, we focused on many things. It's a highly parallel interdisciplinary project, but I guess that the background I've just shown you gave us the sort of the confidence and the impetus to go out and see whether this 30 years of theory on marine cloud brightening holds up and plays out how we expect it to in the real world. And so this was done very much hand in hand with the regulator. And one of the things that the regulator told us very early on was, we don't want you doing this research somewhere else and then just showing up in 5 or 10 years' time and saying, hey, we're ready to cloud brighten the Great Barrier Reef. We want to be a part of the process right from the start, and so and we want you to expand gradually, do a small study, and then upscale a bit, and upscale further, and that actually suited well the sort of natural path of the engineering development and methodology development and the science development of this work as well. So you can see this is what one of our more recent campaigns has looked like. Oops. We have obviously a ship with the marine cloud brightening equipment, the ARIA system, atomizing seawater at about a rate of about 10 to the 15 or so aerosols per second now. It was smaller way back in 2020 when we did the first study. But you can see here how our sort of studies have naturally expanded in scale and scope. And so we started off with drones measuring the plume and characterizing the aerosols and its dispersion, moved to sort of mapping whether or not that aerosol actually makes it up to cloud base and is ingested into cloud, because that was a major uncertainty back a few years ago. And then we've now, over the last couple of years, expanded to actually measuring in situ the response of the cloud microphysics to the marine cloud brightening. So this is some of the kit, and the bottom right panel there is actually not part of the marine cloud brightening system. That's our fogging system. But just to give you an idea, to run those two cannons there, which together give us about 10 to the 15 aerosols per second, we need so much compressed air that we have 2 shipping containers filled with these high capacity large air compressors, because the gas to liquid ratio is relatively close to 1. And so the mass of air is really quite large, highly compressed, and that's most of the bulk of the system and most of the energy cost and most of the weight. We then have a third shipping container, and we've got 2 shipping containers of air compressors. And I don't know if you can see my hand still, but the pump to supply the water for this process is only sort of the size of a high pressure pump you might have in your high pressure washer at home or something. It's an incredibly small amount compared to what's required to provide the air using this particular technology anyway. And so it's, I guess the other thing to point out here is that it's a small industrial plant, right? I get emails all the time, hey, can you lend us a cloud brightening machine? Can you build us one? Can you ship us one over to borrow? But this is not a sort of a very simple machine with just a big green button and a big red button to start and stop, right? It's a small industrial plant. There's 45 minutes or so of safety checks in the startup procedure, and it takes a small team of professional or trained people to operate it. And there's obviously a lot of inherent safety aspects as well. You're using hundreds of kilowatts of electrical energy out in the seawater environment. You've got high pressure air and water. It's something similar to the pressure in a scuba tank flowing right through the system with lots of potential points of failure. So it's I think a lot of people tend to sort of underestimate the complexity of the seawater atomization side of things. And then to study that, unfortunately, we didn't have a cloud microphysics equipped aircraft in Australia any longer. CSIRO used to operate one way back in the 50s or 60s. So we had to go out and sort of develop that platform from scratch, which was really quite a lot of fun. But we now have a cloud microphysics and aerosol and meteorological sampling platform that has really been designed from the ground up for marine cloud brightening studies. Obviously has a lot of other potential uses as well. But everything was selected, including sort of the particular aircraft platform that allows you to fly very slow and at low altitude safely because of the centerline thrust design. So there's a propeller at the front and one at the back in this particular type of Cessna, which means if you have an engine failure going slow at low altitude, it's much safer than sort of any other twin aircraft. But that's allowed us to collect all of the most exciting data that we've gathered the last couple of years. So here I just include a little video of a sampling pass of the aircraft, just to give you a sense of the sort of scale of where this research is up to, right? We're still got a single vessel making a single plume and really doing fairly fundamental science about how that interacts with the cloud physics when it gets there. We're a very long way from sort of scaling up and cooling down the ocean, right? Which is another common misconception. We're still at that very sort of starting block phase of looking at, could this work and how well could it work, and does the cloud respond as well as we thought it might, and do the models adequately represent these processes and capture the response. But I'll just play the video. And so this is a particular pass is sort of just below cloud base or just in cloud base to capture that ingestion of the aerosols into the cloud. And so because aerosols are ingested in these types of clouds from the bottom and then work their way upwards as the activation processes and condensation or growth play out, we tend to sort of sample just underneath to find out what's going in, and then we do passes up through the cloud to follow those processes as they evolve within the cloud. And this is some of that data. So this is from the LiDAR on the ship at the bottom here, and this sort of just was to really address show clearly how the plume goes up, and then you can see the cloud base as that horizontal LiDAR returns there at about 1,000 meters in this case, and the plume sort of quite nicely reaching that altitude. And then the top two plots are sort of interpolated maps from aircraft passes around the area just below cloud to map the spatial extent. So the bottom's an elevation, but the top two plots there are kind of like a plan view, like a map view. And showing that with this single plume, we sort of, impacted the cloud over an area of something roughly like 10 by 10 kilometers in these experiments. And we're able to, I suppose, the other point that's relevant here is that this is sort of at cloud base, and you can see from the concentration plots there, we see quite high concentrations of aerosols reaching the cloud under these sorts of conditions of as many as 1,000 or so per cc. Here's some modeling by Fabian Hoffmann's group over in Germany of marine cloud brightening in a cumulus cloud field. This paper's out now in a preprint. I think the review process is just about finished now for that. But what I wanted to point out with this work is that you can see really clearly here in Johannes's modeling that what we're seeing is I guess again at the top a plan view and at the bottom an elevation, and the clouds are obviously in green here, and the sea salt aerosol plume we're creating on top of the background in the orange, and the purple returns there are showing where the aerosol are impacting with cloud. And I'm sorry it's running so fast. It normally goes slower. I don't know why it's going so fast today, but if you can cast your eye across it really quickly, I guess what I want to point out is that because of the current scale of the experiment, it's a little bit like finding a needle in a haystack in the aircraft, right? We're not brightening entire clouds that we can know that, well, not typically. Occasionally we've had some cases of that, but typically we're not brightening entire clouds that we can then go and compare against a background cloud. We're having these aerosols get ingested in parcels into cloud, and as the cloud moves further downwind and keeps growing, it starts ingesting regular background air again, right? So then we might have a cumulus type cloud with a parcel of within it of cloud droplets that have been impacted by that aerosol, and so it's quite challenging because of that aspect, but also just gives a sense of sort of how it works, I think. I'm not going to show a lot of the results, just partly because they're going into papers right now, and I'm aware this presentation's being recorded, but I'll show sort of a teaser here. Essentially, what we're seeing is a very strong Toomey effect, especially when the background is quite clean. And so, if you have a look at the bottom left panel here, that's just plotting the average number of droplets per against liquid water content. So if we think to the Toomey effect, what we're expecting to see is a larger number of smaller droplets for the same liquid water, right? Which is why we've plotted it up this way. And you can see fairly clearly there the red is the seeded cloud, and the green the background cloud. So we're seeing that increase in ND is droplet number, cloud droplet number. So we see clearly that increase in cloud droplet number. And if we look at the size distribution of those samples over on the right there, you can also see very clearly how that size distribution has shifted with the seeding, right? So in the green there, we have a sort of a trend towards larger droplets and less of them, whereas the seeded cloud has this real peak in the smaller droplet diameter there, or the seeded samples of cloud, I should say more correctly. So I'm not sure how I'm going for time, but not too bad, a little bit slow, but I'll just talk a little bit about the sort of governance aspects and the stakeholder engagement, and this is my last couple of slides. But I mean, I think one of the reasons we've had such a high level of success in the RRAP program doing this work, which can be quite controversial, is that we really from the very outset worked to have an exceptionally high level of community, stakeholder, traditional owner engagement. Over the last 6 years, I think I've probably spent more time on the engagement side of things than I have on the science, and that's been very rewarding. Has slowed the science down a little bit, perhaps, but the science couldn't have happened otherwise, right? And it's just so important. And when we talk about engagement here, we're not. This isn't educating people about what we're doing, right? This is sort of genuine two-way engagement where we're talking to communities, we're talking to traditional owner groups. This is a community panel made up of ordinary citizens up in the Great Barrier Reef in the Townsville area, that one, and asking them what are their views on their research, what are their aspirations for this research, how would they like to see this research done, and that feedback is then having a direct influence on where and how we conduct the research and how we communicate it. Obviously, we're also fortunate, I think, to be operating in a one of the world's most highly regulated marine estates. So there's a very high level of oversight from the federal regulator. We need a permit for everything we do. That permit process often involves various levels of consultation of its own, separate to us. And then each field campaign, we have to produce a report for the regulator. They do their sort of risk assessment before we do the work. Then they look at the results and what happened and reevaluate and decide whether they want to give us permission to sort of go to the next level. And it's like that every step along the way. Also internally in RRAP, we have our own governance structure, including an a board that's made up of one member of each organisation involved, plus independent members, plus an independent chair, plus an independent traditional owner representative. And so all those decisions are sort of very open, very transparent, and with a very high degree of rigour and sort of independence from the researchers that are promoting their various experiments and avenues of research within the program. Part of our program, which I haven't talked about much just because of time, is also a large focus on social science and understanding the social, the regulatory, and the governance landscapes around this work. But just to give you a sense, this is one of the early surveys of the Australian public, I think back in 2019. And I really should update this because they've just very recently published a more updated survey, taken some years later. But basically, back in 2019, a social scientist will tell you this kind of a distribution from a survey means that people don't tend to know enough to make up their mind very strongly. It's not polarized. It's not strongly skewed either for or against. Basically, people are still a little bit on the fence, but fairly encouraging. There's a bit more of a center of mass there towards sort of accepting of this research than against it. And I am pleased to say it's not a huge shift, but the more recent survey does shift that even a little bit more to the right, I think. So it's not a big shift at all, but it's headed in the right direction, I guess you could say. And the last slide here on what's next. So as was mentioned in the introduction, we've now received some funding from the UK government for a project. And maybe we can talk more about this if people are interested in the discussion. But the results I showed sort of really sort of prove over the Great Barrier Reef this to-me effect. But we're very interested next in all of these second indirect effects of aerosol on cloud. So how does that cloud that you've now changed the droplet size distribution within, how does that then play out over time with all these other cloud processes that could now be altered because you've fundamentally altered the cloud? And we expect that some of these processes may increase the net cooling from the perturbation that we cause. But it's also potentially that some of them reduce and go against that sort of initial brightening by, for example, making the cloud easier to evaporate so it sticks around less time. We think overall probably these effects are going to add up to be an increase in net cooling. And some people get a bit too hung up on this, I think, like, potentially some of these second order effects could undo the initial brightening. And under certain atmospheric conditions, that's certainly the case. It's certainly possible. But we also know that the overall net effect of additional aerosols on low cloud is very much a net brightening, net cooling effect. And we see that with the ship emissions, for example. Apologise, I went a little longer than the 30 minutes.
Not a problem, Daniel. Thank you so much. It was indeed really stimulating and right on target with what our members would be interested in learning more about. I'm sure the members have a lot of questions, and for those interested in posing a question, as usual, please raise your virtual hand and we'll get started with the Q&A. Let's see. We have, I believe Jonathan Cole is first in line. Jonathan?
Thank you. Wow. Some members of our group have been waiting a decade for this exact presentation.
Whoops.
I wonder,
Dennis, do you
is
need
that
to turn off your speaker? There we go. Anyway, this is a marvelous presentation.
We have a bad feedback. Everyone turn off your audio.
Yeah, I'll keep talking and hopefully it'll disappear. It looks like it might be gone now.
Yeah.
Okay. Anyway, this exact presentation is what some of us have been waiting for a decade. So such admiration and applause. Thank you so much. And I know that a lot of people have a lot of good questions about marine cloud brightening. So I wanted to edge in a separate question first. Just if you could give a moment to describe the results from your floating film simulations and testing, and were you encouraged that it could have as much an effect of cooling the ocean water as the marine cloud brightening had?
sure? So I'll have to preface it, I think, with a little bit of an explanation about the fundamental difference. So, at least in RRAP, and this may not be true of all applications, but there's we believe two ways to help the coral. One is cooling down the water, but corals actually bleach as a function of light stress in the presence of higher temperatures. And so, to give an example of this, there's been some sort of fairly well documented cases where in the Pacific, there in the Coral Triangle, might have an island and it's recently rained or something, and there's a lagoon area that's very, very turbid, the water, and a mass bleaching event comes along. And even though the corals that are in the very turbid water experience the same temperatures as the corals that were on the outer fringes of the reef, the corals in the turbid water are fine, while the ones on the fringing reefs all bleach and die. And I guess without taking up too much time, I mean, I don't know where the interest lies here, but I'm assuming it's not coral physiology. So without getting right into the coral physiology, I'll try and make it quite simple. I think up to a certain level of heat stress, if you can reduce the light, even though the heat stress is still there, you can prevent the corals bleaching or reduce the intensity and mortality resulting from that bleaching. So in the cooling and shading program, we essentially have these interventions kind of almost divided into two groups. One that are at very large scale, like the marine cloud brightening, that might be able to cool the water over large areas, or pumping up cold water, which are obviously also targeting cooling. But then we also have this set of interventions that we think if you apply over quite a limited period of time during the doldrum conditions, when the light and the temperature stress is really the most severe, and that's what tends to over a summer push the corals really into bleaching. If you can, we think if you can shade them just during those fairly short periods of time, we can mitigate some of the bleaching and mortality. And so the surface films fit into that category. So we're really focused more on the shading aspect and the actual cooling of the water. It's hard to cool the water in a very limited spatial scale because it's kind of coming in and out as fast as you can cool it down a bit. I mean, it might be different in some certain, like an enclosed reef at low tide, for example, where the water is resident, just sort of sitting there like a pond, might be a different story. But generally speaking, the water is able to cool down in the marine cloud brightening scenarios because you're doing it over a large scale, and that small reduction in light intersects with the water residence time in that kind of shallow but large Great Barrier Reef lagoon. So the surface films, there is I think there's at least two papers published on the surface films now. One's a modeling study, the other is some of the experimental results. And I think they were able to reduce light by about 30% or so. But because the anticipated scale is is really quite small, sort of over a snorkeling type site or something to protect kind of high value reefs. We didn't really, I don't think anyone's really looked into how much the water would cool down, but I think we'd expect it to not be a lot under most circumstances.
Okay, great. Thank you.
Yeah, thank you. I think the source of our feedback is Ron Bayman. You have two devices, and I think if you turn on both of them at the same time, you're going to get that feedback. Our next questioner is John McDonald, then Robert Tulip, then Mike McCracken. John?
Hi, thanks, Dennis. Hi, Daniel. We met in Canberra a number of years ago, and congratulations on this great progress. I mean, and thanks for the update. I've got a strong interest in both MCB and surface reflectivity, and been looking at autonomous solar thermal devices that nanobubble platforms particularly, and also ship-based nanobubble generation. I mean, it's got to be scalable. The beauty of ships is, of course, you can use all the waste heat from their engines to, and I'm concerned about energy consumption. Of course, we've got plenty of ships steaming up the east coast every day outside the reef. They could quite effectively do it, but the benefit is you can also get hull efficiency from reducing the friction with nanobubbles under the hull, of course. So that helps to pay for itself. So I've been focusing on those, more recently, probably more towards ocean whitening. So just following up from Jonathan there, interested in your comments there and the energy consumption side of things. Thanks.
So I think you might have noted, I hope it was in that slide. So I guess ocean whitening was certainly one of the things that's within scope of the cooling and shading program. It wasn't prioritized for research funding, so it hasn't been progressed much by our group. So just to explain how that sort of works is that there was that initial whittling down of ideas, but the ones that remained in, because they weren't sort of ruled out, weren't necessarily funded. There was a process, and I guess prioritizations had to be made. We received far less than the budget that was originally asked for to the government, and so we could only focus on certain things. We also hit a bit of a resources limit of just not being able to find enough scientists to work on this quickly enough. But so there was. I think the two things that kind of led to micro bubbles or nano bubbles not being sort of prioritized for research were, on the one hand, at least 5 or 6 years ago, no one had really shown the sort of technical feasibility or any sort of demonstrations of technology that would be able to create enough bubbles that the sort of back of the envelope calculations indicated you'd need to provide sufficient shading over a sort of a reef area. And we did look at it more from that sort of, could you do ocean whitening at a strong enough level to get to that sort of 20 or 30% shade level, rather than a really widespread regional application. And then there were, I guess, other things like the sort of surface films which were already demonstrated to be able to achieve that. So the sort of focus went there initially. I think the other one was that there was a concern amongst the coral biologists that the bubbles could be harmful to coral or to parts of the coral reef ecosystem. I can't really comment too much on that because I never really saw any kind of actual investigation into that or evidence to support those concerns. But certainly there were some coral biologists that were quite concerned about that, and I think that sort of even I suppose, like I said, with the biogenic oil fogging, even a perceived risk or concern can sort of be quite detrimental, I suppose, if the social license isn't there. So I think a fair bit of work was needed in the area of microbubbles to sort of further investigate the feasibility, and that work was just not prioritized yet. But that doesn't mean that sort of RRAP has a position that it shouldn't be. We just had to make a judgment call on the resources available.
Okay.
Yeah, it's like an ideal project for AIMS to take up, the sea simulator.
Yeah. And the question on energy consumption for the MC.
Yeah,
sure.
Thanks.
So, well, look, I think our current machine uses roughly 300 kilowatts or thereabouts to produce 10 to the 15 aerosols. But I guess I'd strongly caution against making too much of those numbers because, you know, I guess like I tried to explain, we designed and pursued and developed a technology that could get us out there experimenting on clouds as quickly as possible. And so I suppose you could call it good enough. And for being able to, I guess our focus has been on really first understanding whether the clouds are even susceptible, right? And will they respond how we like? So certainly now attention has and needs to shift to finding the most energy efficient nozzle technologies to be able to atomize seawater. But that really hasn't been our focus, right? And so I really would like to strongly caution against these sort of, and I've seen them floating around by some people where they sort of just go, okay, well, Dan's machine needs this many kilowatts of energy and it produces this many aerosols, and if we, times that by 1 million to do the whole world or something, it'll be this much energy. That sort of calculation is really missing the story completely, right? You wouldn't take what we have now. If what we have now is all that was available, then you can forget about trying to even do the Great Barrier Reef, let alone the world, right? That's not how it works. But we do have a quite a intensive research program. Well, actually, it's smaller than I'd like, but we've got one postdoc and another starting soon, and a couple of PhD students here at SCU working on, finding nozzle technologies that are much more energy efficient and produce a larger number of aerosols. And under our ARIA project, we're sort of hoping to sort of, maybe reach a 5 or 10 times increase in the energy efficiency of the nozzle. So sort of, I guess a step-by-step with kind of interim, efficiency goals to hopefully get us there. I think we need to do the Great Barrier Reef. I think we need about a 30 times increase in energy efficiency based on some of our most recent modeling. And we might have already recently found close to 3 or 5 times just over the last few months. So then that means only maybe another 10 times from where we are now. But I do think it'll be a sort of an iterative process to get there, unless somebody really stumbles across something that just outperforms everything else that we haven't tried yet.
Promising.
Thanks.
Well, Robert, our next questioner.
Thanks so much, Daniel. It's just superb that we have this opportunity to engage with you, and I hope that it's something that we can continue, because your program has often been mentioned as the only field test of geoengineering technology. That's like, you look back to Scopex and then the Alameda disaster. Like you've obviously been able to do something that's been able to avoid the barriers that some of those other projects have had, which is congratulations on doing this. I thank you for the information about the scalability challenge, and so that question of the research that's going into particle generation, just getting the particles small enough and equal enough. Like Stephen Salter commented that was just going to be a really key research agenda, and so that emphasis is really valuable on the cost side. And I'd just like also if you could comment on the controversy aspect that you touched on. Just seeing the slide that you showed of the social acceptance was very heartening, because there's a lot of controversy around geoengineering and the question of whether you characterize your program as something that's that points towards the eventual potential to restore planetary albedo. And a further question: just what's the potential if you just cool in the territory of the reef? Then what's the risk that hot water from the open ocean is just going to come in and overwhelm that cooling effort within the reef?
Sure. So look, well, I mean, I certainly wouldn't characterize our project as geoengineering, right? Yes, we're using a geoengineering relevant technology, or even you could call it a geoengineering technology, I suppose. But I think in really a lot of it comes down to sort of intent and the use case, right? Just because you could use a technology to cool the planet doesn't mean that the risks, the social acceptability, or the potential benefits are the same as sort of using that technology, intermittently on a regional scale to mitigate coral bleaching, right? I really think that they're quite different. And I think that does have a lot to do with the social acceptability of our research. People are relatively sensible for the most part, and can understand, I guess, the difference in potential risk between something that's sort of applied intermittently, during a marine heat wave over, I mean, even if you did the entire Great Barrier Reef, it's something like 0.07% of the globe or something. And we're looking at scenarios now of doing much less than the whole GBR, because doing the whole GBR would be so expensive, and you probably wouldn't start with the whole GBR. So I think the benefit risk equation is very fundamentally different. And I think people are kind of comfortable, or more comfortable, let's say, with being able to evaluate that kind of, for themselves, their own attitudes to that sort of benefit risk equation, or potential benefit, potential risk. I think the general populace is much less able to, or don't feel that they probably have enough information or enough understanding to do that as well for the sort of alternative scenario of trying to cool the planet. So I think a lot of it boils down to that. I think, and I think it should, right? I mean, in my mind, whatever you're proposing, the sort of the risks need to be evaluated against the potential benefits for that particular scenario and that particular use case. So I wouldn't really consider, this use case and the research we're doing to be geoengineering itself, but certainly, I guess, some of the lessons and some of the technological and fundamental science. Well, there's lots and lots of aspects. Some of the methodologies we've developed and things can all sort of potentially be applied to other use cases, of course.
So what does that imply for hot water coming in from the open ocean to the reef?
So hot water coming into the open ocean. So this is, so I'll try and explain this a bit better. So, if you take take the scenario I showed you guys that we've modeled, which was a scenario where you did do sort of essentially cloud brightening over the whole Great Barrier Reef Marine Park. There's also an associated scenario where we did marine cloud brightening over the whole domain. So the domain of that CSIRO ocean model for the reef goes way out into the ocean, and basically, it's a scaling of the area that you're impacting the cloud versus the water residence time, right? So the bigger you go, the more cooling you get. But probably the only reason this works well in this regional sort of scenario when we're thinking about cooling, I mean, we have the right atmospheric conditions too. We don't have the best clouds, but we've got clouds that appear to be good enough. But in terms of the ocean cooling, Yeah, the Great Barrier Reef, it's very shallow, right? It's sort of the average depth for that whole Great Barrier Reef lagoon is only about 40 meters or so. So if you think of like a puddle of water on a beach or something on a hot day, there's limited exchange of water in and out of that lagoon. And if you if I brought back up that slide where I showed you the modeling results, when you start the scenario, so you assume that you start marine cloud brightening, it takes the water anywhere between sort of 4 and 6 weeks to cool down, and then like relative to the control, really you're avoiding the warming, but we'll just for simplicity, we'll say we've cooled it down, and then it kind of levels out, right? And that's because at that point you've matched the warm water coming in, getting cooled with the cooled water flowing out. So it's a I guess it's a fairly well-known kind of concept in oceanography and hydrodynamics, but it's a relationship with the water residence time. So what's the average amount of time that water spends in that area getting cooled down? And that basically sets the amount of cooling that you get for a given forcing. And if you then increase the spatial area, you're increasing the water residence time, because now water's got the average amount of time that the water spends in that area is more, and so you'll cool it down a bit more for the same amount of forcing. So the hot water is constantly coming in. These model scenarios, we've run them in hindcast over several previous bleaching events. One of the fairly remarkable things that we found is that I expected there to be really big differences year to year, sort of El Nino years, La Nina years, and also I expected there to be big spatial differences in sort of the cooling. But it's really quite interesting. One of the big findings of all that work, I think, was that it really sort of averages out. You might have more cloud in some months and less in other months, or you might have more cloud over the south of the reef, but the water flows north, and between the heterogeneity of cloud cover and susceptibility and the circulation within that area, it does tend to kind of average out fairly evenly, which was actually a big surprise to me.
Okay, thank you, Daniel. Very comprehensive. We've got 4 more hands up, and I see time is going. We'll have to, shorten up the questions and shorten up the answers
Sorry.
a little bit if we're going to get through. So next is Mike McCracken, our chief scientist.
Okay. Thank you. That was very interesting. I guess what I'm interested in most is the studies I thought that had been done by, for example, University of Washington and other things, and people were saying you could have too much CN, you could have too little, you could sometimes lead to less clouds or more clouds. How dependent did you find it, your results, on the meteorological conditions, and did you adjust for that? So if you went to out to try and do it as a global effort, would you have to have a lot of detailed meteorological information about each location you're doing it or each area in order to get the right amount of things done and not come out with reducing cloud cover and causing more rain?
So, now I have to give a short answer. This is a bad question to have right moving into the short answer phase. I think the short answer is we don't know enough to probably give too confident an answer to those questions, but I think we know a fair bit. I think probably a lot of those aspects that you mentioned really speak more to optimizing the effect rather than getting the effect. I guess, like I mentioned before, all of the global ship emissions, I didn't show it. It was one of the things I took out to shorten the presentation. But if you look at the IPCC energy budget for the Earth, right, and the negative forcing from clouds and aerosols, there's a lot of uncertainty, but it's all to the left, right? It's all cooling overall. So I think that's sort of a pretty good analogy for the answer to your question. There's a lot of uncertainty about exactly how big the effect will be in different conditions, and there's probably some unusual well, I don't know about unusual, certain types of meteorological conditions and clouds that you'd want to avoid. But I think we have a basic to reasonable level of understanding already about what those are. I guess to be confirmed, from experimentation and better modeling. That's more, less theoretical and more closely tied to some experimental results. But I think in the big picture sense, some of that's kind of getting into the weeds. The droplet size distribution or aerosol size distribution that you use has an impact on some of those processes too. And so I think initially you're probably pretty safe to get cooling with a pretty broad droplet size distribution outside some relatively unusual circumstances. But then as you move along in the sort of, I don't know, maturity of the technology, you certainly would probably start to tailor things to try to optimize and maximize the effect.
So you sort of had a light mixed clouds in what you showed, but some areas have no clouds, some areas have full cover of marine clouds. So it's quite a mixture of conditions you would face if you tried to do over a large region.
Sure. So you certainly, you could certainly tailor it, right? You could sort of target aerosol sizes that contributed more to what people are sort of calling marine sky brightening, right? Where you target the aerosol direct effect where there are no clouds. The technical feasibility of that right now, though, I would say is exceptionally low, right? Our fogging machine, which I didn't talk about or show today, makes a low-hanging sea fog, but it uses about the same amount of energy as the cloud brightening machine, and it's targeting those aerosols to target the direct radiative scattering effect. And we cover an area only sort of less than 10 hectares with that, maybe a kilometre by a kilometre when the wind is low, but at a fairly high level of shading, sort of 15 to 20% shading perhaps, but still, it's orders and orders of magnitude less spatial coverage than what we achieve with our cloud brightening machines using the same amount of energy. So I just don't see that it's going to be very technically feasible unless somebody can invent a system to really come up with the perfect drop size for sky brightening at a very low energy cost. We're sort of exceptionally far from being able to do that, much more so than the cloud brightening.
Very good, Daniel. We have 3 more questions and 20 minutes left. If you can continue with us for a little while longer. So we have John Dixon is our next questioner. John from Down Under.
Yeah, thanks. Thanks, Dennis. And look, that was terrific, Daniel. Like the first speaker, I was really looking forward to this presentation, and you did well for us. I'm glad that you just covered fogging, because that was going to be one of my questions about feasible pathways forward. And so that's excellent. But very early, I want to go to 2 spaces. And very early on, you spoke of interactions with other effects, and you touched nutrients. And there were active programs to reduce nutrient inflow. Has that actually had any slowdown of bleaching effect from your observations? So that's one space. But the bigger and more important one I've got is related to the stakeholder engagement in the region. And I think my perception is we've got external funding, national or international now with ARIA, which will keep a modest team together for a few years. But I wonder whether you've got any feedback from those most economically affected by the reef, and I'm specifically thinking about the tourist operators. Have they actually shown any interest in stumping up and funding some of your staff or researchers, or in some other way assembling data or placing sensors in areas that would help you? So that's my bigger question. I'm hoping that the ARIA work will enable the stakeholder groups and the governance system to continue. So over to you, Daniel. Well done so far.
Thank you. Yeah, look, you ask at an interesting time. We're still waiting to sort of find out the implications on the RRAP program of the latest federal budget. What parts will be going ahead? Certainly, what we proposed for a second phase of RRAP hasn't been funded in this federal budget, so it's not clear what components, if anything, will be going ahead for RRAP. So our RRAP wraps up in 30th of June this year, so very shortly. And so we've been waiting for this federal budget. So it's only now that we really sort of have to strongly turn our minds to those questions. As far as the stakeholder engagement under ARIA, we do have planned over the remainder of this year, starting in, I think, early August, a very large roadshow all through northeast Queensland, taking our researchers and our science all to community groups, stakeholder groups, traditional owner groups right along the coast of Queensland. So that's a really big activity planned for the rest of this year. To sort of communicate, where we got up to in RRAP and seek input from the community and things about where to go with ARIA. So there'll be a real chance for those conversations coming up. What I can say is that the tourism groups that we've worked with have been incredibly accommodating so far. We did one of our field campaigns out of Hamilton Island and based the aircraft there, and they were just amazing. They gave us accommodation and golf carts to get around the island and everything, and sort of really fully supported our research. But it has been a little bit ad hoc so far, and this road trip that we're about to embark on is kind of a bit of an effort to more thoroughly consult with those stakeholders.
Good, excellent. Might be important going forward.
Always important.
And fingers crossed on the federal budget. Who knows, huh? What the details will be revealed in due course.
That's right. We're still waiting for a kind of an announcement from the minister or something.
You're on mute, Dennis.
Ron, very short question. You're on mute also.
Yeah, thank you. So thank you, Daniel. That was very, very inspiring. I mean, as many others have said, you guys are doing the work. A lot of people are talking, and you're really trying it out. So kudos to you and the Australian government and all the other partners and stakeholders who are working with you. My question was about the IMO regulations, as you might imagine. I'm wondering, we have an open letter published in Oxford Open Climate Change a couple of years ago, and we just asked the IMO to consider possibly maybe trying to maybe allow some of the sulfate aerosols in the high seas and work on finding alternatives for non-fossil fuel emitting ships. And so far we have been absolutely unable, stymied, to get any, basically all the nations in the world are members of the IMO, many of the large NGOs. Nobody seems to be willing to just ask the IMO, it's the Marine Environment Protection Committee, whose chair, their chief scientist, I gather, of the IMO, has actually encouraged us to find somebody to submit this, because she said, yeah, this is, I think this is something we should look at. So my question is, I don't know that you, but Australia, this looks, the early slides that you showed, oh, okay, this would be something that perhaps Australia, I've been, we thought small island states, we tried all kinds of folks, but is there any chance that you or others or people that might be able to encourage the Australian representative to the IMO to simply ask, just submit our published paper, peer-reviewed, and over 20 some studies earlier than the ones you mentioned, but all saying that this was a warming termination shock, when those regulations went into effect, and now they've also doubled down because they've done them in the Mediterranean as well. Just to look at this, try and consider maybe there's a way to offset this. So it's just a suggestion.
Mhm.
I think, I mean, it would be my personal view that putting sulfur back in the fuels is probably very unlikely. I mean, I think maybe advocating for, I mean, certainly I think the action and the repercussions of it were probably something not that the IMO kind of foresaw or expected. But I mean, I don't have any direct contact with the IMO, so I can't really speak to their attitudes and things at all. But I mean, I think maybe advocating for at least research into whether adding sea salt aerosol production to ships as a more benign method of trying to replace some of that lost radiative forcing would sort of make sense to me. I think there's a pretty solid argument there. I think that the sort of the fundamental issue maybe that your question is getting at is really sort of stems from the fact that science moves very slowly and certainty in science is nearly never reached, right? And so it's a very slow process probably from action to finding out and being confident enough, because I mean the global climate is inherently very variable, right? And very heterogeneous, and it's very hard to it takes quite a while to really apportion that response to that effect. It's it's a slow process in the peer-reviewed scientific world, and so because of that, you probably have trouble in the shorter term getting the IMO to do something as drastic as putting sulfur back in the fuels.
So that would be that would, I think that's part of our proposal. But by the way, there was a study early before the regulations went into effect that said you get most of the health effects and most of the cooling effects if you did this, if you relaxed it in high seas and just did it in emission control areas. But so there is some scientific basis. We say, why don't you study this further and find out, and possibly do this, but also work on, as you said, other alternatives. And just to follow up on that, one of our concerns as a group is the urgency. We don't always need to reduce all the uncertainty to start, doing what we can for cooling, because the alternative to not cooling, we know for certain, is a disaster. So, I think the balance here, and many of us are trying strenuously to address that balance, say, this is an emergency situation. We should be in a wartime footing trying to cool the planet as fast as possible, because we're running up against really calamitous possible risks. We're certainly increasing those risks of very, very calamitous events for human civilization. So it's not the time to be, trying to futz around and get perfect science and on every single thing. There are many cases where you could just try things and see what works, and as you're doing to some extent, just keep moving gradually and adjusting as you go along without necessarily knowing ahead of time what all the what's going to happen. So anyway, I'm sure you're aware of that. I don't want this is like preaching to the converted, but thank you very much.
Thank you, Ron. And it's interesting, the analogy of what Daniel is doing on the Great Barrier Reef and what we hope can be accepted in terms of pilot testing of stratospheric aerosol injection, trying it out on a small scale and looking for its benefits and risks. Well, we have just a few minutes left, but we have one last hand up. So we'll retain just our last question from Seb Clark, also from Down Under.
Hi, Daniel. I think there are about 6 challenges remaining for you to have a successful program of cooling the reef. Can I go through them and you check me off whether I've got them or not? First one is the aerosol size distribution at the moment is suboptimal. I think you may need to have smaller aerosols and maybe not so much larger. I'm not sure. That's one. Secondly, there's a you said we're getting about 10 to the 15 ccns per second, and you need to have about 10 to the 17th. Is that right?
Somewhere between 10 to the 16 and 10 to the 17. It's cheaper to do it if you can have 10 to the 17.
Yeah. Third is the making the aerosols is too energy intensive. You've got to go that, you said you want to get that down to about 30 times less energy. So that's quite a big one.
Yep.
Another one in my mind is that you're using expensive crewed ships to do this. And that to me is maybe not going to be an economical solution for trying to do the whole of the reef. The fifth one is you require special conditions for your system to work, special conditions of humidity. And so if you can find another way to get the right humidity to engender the humidity, then your method can use to go through many more areas than what it's at the moment. And the final one is you're using fossil fueled energy to power it. And I think we've got to go renewable. How does that match with your set of problems?
I can see where you're going with this, Sev, but so look, the size distribution, I guess I go again back to that earlier question. I mean, we're seeing quite a strong response in the clouds with the size distribution we've got, right? I think it's I think certainly optimizing it is very desirable. Yes, but is it necessary? I'm not so sure. But we're constantly working to try to get a better size distribution. Actually, at the moment, out of our particles that we're producing, we think about 66%, so 2/3 are in the right size range. And the other third basically is too small. We're not with the particular technology. I mean, we're actually testing a few different technologies, but that would have made a much longer talk. But the one that can produce the most aerosols is the one I showed. And we're not too worried about the large ones with that particular technology. Other technologies have a different problem. They have a larger median, but also a longer tail into particles that are too large. So anyway, yes, lots of ongoing work to do on the size distribution. Don't disagree, but also don't agree that it's absolutely necessary to get a cloud forcing. Yep. 10 to the 17 is a good target, makes it a lot cheaper. Happy to agree with that. Energy intensive, yes, obviously it's not. We talked about that. Crude ships, well, we can consider alternatives, but I would mention that the Great Barrier Reef Marine Park Authority is in no way, shape or form anywhere near letting autonomous vehicles cruising around the Great Barrier Reef, right? Because of the risks of collisions and damage to the reefs and things. It's a hard no.
But you might have stationary platforms. Stationary
platforms is something we've looked into, yep. But they have to be manned. You can't even leave them there. Right, you have to convince Gurumpa that you can get them out of the way before a cyclone comes through. So that needs to be taken into account. I didn't quite understand what you meant about special conditions with relative humidity. The ingredients you need for the cloud brightening to be effective are basically low background aerosols. And somebody asked about this before, and I didn't really get to address it, I don't think. But certainly, the effect is it becomes less pronounced the higher the background aerosols until there's no effect at all, right? Because once there's sort of plenty of aerosols to activate, adding more makes no difference to the cloud brightness. So low aerosols, boundary layer associated clouds in that low aerosol environment. The higher the cloud fraction, the better. Same with thickness. But then there is all these, second order indirect effects on the cloud physics that we need to understand, and that could change that equation, right? You might find that overall, you what you thought were the best conditions because they give you the best Toomey effect are not the best conditions overall, or you might have to sort of further subclassify that into whether you have a dry atmosphere above the clouds or a more humid atmosphere above the clouds. It's too complicated to cover now, and there's many aspects, and I'm not an absolute expert in that. And then the last one, yes, would definitely be desirable in an implementation scenario to not be using fossil fuel energy. Happy to agree. We've done some research into possibilities, and we're continuing to do research into possibilities. Although I would point out that I guess, again, speaking to the urgency, if you had to have, say, 25 ships out there to cool a sort of, target region of high priority region of, say, 13% of the Great Barrier Reef, I mention that because it's a scenario where we're running. Would you accept an extra 25 ships worth of emissions to stop 13% of the Great Barrier Reef bleaching every couple of years? I'd make that argument, but it's not ultimately my decision. That's tied up with the social license, right? But the argument I'd be making is that given the state of things, I'd accept that fossil fuel penalty to keep the corals alive. But others are free to disagree.
Good.
But yes, of course. Look, we've published a paper now with one of our PhD students who looked at this question, and in the immediate short term, what he found was the most sort of practical and viable in the shorter term was that you could reduce the emissions by 60% if you sort of had photovoltaic solar panels, a battery system, and a sort of computer controlled diesel power source. Unfortunately, having enough solar panels to just do it entirely solar paneled is not really feasible. But having the sort of amount of solar panels you could have on a ship, and this battery system that kind of really works to minimize the emissions of the diesel power, you could get emissions down 60%. So that's kind of encouraging.
Good.
All right. Well, we're just about at the end of the 1.5 hours, and on behalf of all of our members, I want to thank you, Daniel, for joining us today. Your remarks were very much appreciated. Your approach is a great model and a great inspiration to us all. And so you must keep going on this. And we wish you the best of success in your efforts to hold on to your federal budget funds, for one thing. And we shall avidly be following your work and also communicating your successes globally as a great example for MCB application. So once again, thank you, Daniel, and we'll stay in touch.
Thanks very much. Nice to meet you all. Bye.